recording. Okay, so it's a great pleasure to have Johanna Knapp from Melbourne. She's going to tell us about GLSM localization and the stringy Kahler moduli space.
So yeah, thank you very much for the invitation. This is a great seminar series, so I'm very happy to speak. So I'm going to report on 2 papers from this year. One were in collaboration with Mauricio Romo and Emmanuel Scheidegger, who are both in the audience, and one with my PhD student, David Erkinger, who, by the way, is on the market this year. So this is the outline of my talk. I will start off with an overview, which is more or less an executive summary of the talk. And then I will spend the rest of the time filling in the details of the main results. So after this overview, I will go to gauge linear sigma models and localization and recall the results that we're going to use. And then I will present first our results on the hemisphere partition function, which is the first paper, and on the sphere partition function, which is the second paper. And then I'll have a few conclusions. All right, so please don't hesitate to ask questions. I'm also monitoring the chat window, so please ask. All right, so let me start with the overview of the general setting that we're going to consider and the problem that we want to look at. So this is more or less classic string theory. I'm considering string theory on Calabi-Yau spaces. So for the purpose of this talk, I will focus on compact Calabi-Yau threefolds in a type 2b, so type 2a or b string theory setting with or without D-branes. And I'm going to focus in particular on the Kahler moduli space that comes with such a Calabi-Yau compactification. And we're going to be after the structures in this moduli space and how to do calculations in particular quantum corrections. So what I've drawn here is a cartoon of the structure of the Kahler moduli space of a Calabi-Yau threefold. And there are various features that I want to highlight here. So at first I have to say, because we are in a Calabi-Yau setting, each point in the moduli space will correspond to a worldsheet CFT of central charge 9 or 3, depending on how you want to count the central charge. And this is the Kahler moduli space. So there are different regions in the moduli space. So the generic region, somewhere deep in the moduli space, we will not really have much hope. Well, sometimes we do, but it's very hard to study generic regions in the moduli space because we very often don't have an explicit realization of the CFT at generic regions. It gets better when we are getting to limiting regions of the moduli space. And of course, when you consider string compactification, there is one very canonical region in the moduli space, which is when the Kahler moduli are large and we are in a large volume setting. But the point I want to make in this talk is that these large volume regions, they are actually very special regions in the moduli space. And there are many, many other regions which are not large volume, but still correspond to some CFT associated in some sense to a Calabi-Yau. And some regions that have been studied in the past and are rather well known are, for instance, Landau-Ginzburg orbifolds. And in the first paper that I want to discuss, we focused actually on this Landau-Ginzburg orbifold points. So about these points here, there's also a lot known, not as much as large volume, I would say, but still quite a lot, and both in mathematics and physics. And then there are regions in the moduli space which are still limiting in the sense that some moduli will be large or going to infinity, which are neither large volume nor Landau-Ginzburg, and they still remain quite mysterious. And also their CFTs and also, let's say, a space-time description of these theories is rather elusive. They're usually referred to as hybrid models. So this is one thing I want to say about this. And what I indicated also here is that the moduli space decomposes into chambers. So in a geometric language, this would be some Kahler cones, but it doesn't have to be because we're not geometric everywhere. And the point is now that one can actually go between different, smoothly interpolate between different regions in the moduli space. So you can leave the Kahler cone and go somewhere else, and maybe you want to connect a large volume region to a Landau-Ginzburg region. And that's possible because you can actually go through these walls. And what will happen here in the context of Calabi-Yau is that there is some sort of transition happening, like a flop transition, a blowdown, something like this. And actually, when you look at Calabi-Yaus, which are somewhat exotic in the sense, for instance, that they are not necessarily hypersurfaces in Torriganian spaces, these topological transitions can be quite severe. So they will not change the Hodge numbers, but they can change finer invariants of the Calabi-Yau. So you should actually understand this moduli space as something that connects different Calabi-Yaus. So there is different Calabi-Yaus associated to one and the same moduli space, and you can go from one to the other. And sort of the general conjecture in this context is that you can associate certain categories to certain limiting region, and the conjecture is that categories associated to these different chambers are equivalent. And for instance, for the case of large volume and Landau-Ginzburg regions, these conjectures have actually also been proven, and they have a lot of very deep content. So what I am mostly after in this talk is to study regions that are not necessarily large volume, but using the knowledge we know of the large volume regions. And I also want to do something like, explicit. So I want to be able to, for instance, compute quantum corrections in this setting of Calabi-Yau compactifications. And there in the Kahler modular space, you will have lots of them, because things that you can compute in type 2 compactifications of string theory, like you cover couplings or D-brane charges, they all will get quantum corrections due to worldsheet instantons. And what I want to discuss is how to compute them with the methods that I'm going to use. All right, so what I want to do, or what the goal of the rest of the talk is going to be, I want to study this stringy Kahler moduli space and its rich properties in limiting regions that are not necessarily large volume, and we want to find some structures that are somewhat universal that we may know in the geometry in these more exotic regions of the moduli space. So this is the general idea. All right, and this is the tool I'm going to use to study these moduli spaces. It's the gauge linear sigma model. So the gauge linear sigma model was introduced by Witten, to my knowledge, just for this purpose of understanding these moduli spaces. And it's a 2D 2,2 supersymmetric gauge theory. And one interesting aspect about the gauge linear sigma model is that it provides a common UV description of the conformal field theories that sit at every point in this moduli space. So how does this work? So conceptually, what's important here in the gauge linear sigma model is that it comes with coupling constants. And in particular, it becomes with complex coupling constants called the Fourier-Ilopoulos parameters, which I will also introduce again later. And the point is now that if you choose gauge linear sigma models that are sort of related to Calabi-Yaus, you can identify these coupling constants of the supersymmetric gauge theory with the Kahler moduli space of the Calabi-Yau. So by studying the gauge linear sigma model at different values of the coupling constant, you can actually probe the whole moduli space. And in order to, to comment on this UV description, that means that you take the gauge linear sigma model and you compute its low energy configurations depending on different values of these Fi parameters. And then you will get different solutions to the vacuum equations, and this is referred to as phases of the gauge linear sigma model. And that will actually then give you the descriptions of the CFTs in the limiting regions if you're lucky. So the point is that this chamber structure that you see here is seen by different low energy configurations of the gauge linear sigma model, depending on how you choose the coupling constants. So this is how we can probe the moduli space using supersymmetric gauge theory. Yeah, so this is not a new story. So this is was introduced by Witten in '93 to understand what's called the Landau-Ginzburg Calabi-Yau correspondence. So this is not new, but the new input that has happened in the past few years is results in supersymmetric localization. So you can apply supersymmetric localization to, of course, to the gauge linear sigma model, because it's a 2D SUSY gauge theory, and you compute some partition functions. And it turns out that actually these partition functions, the sphere partition function, the hemisphere partition function, which will play the main role, and also other things, they compute quantities that you are interested in string compactifications that encode, for instance, instanton corrections in string compactifications. And so these are quantum exact quantities, and more or less the parameter dependence, the t dependence of these results, these partition functions you get from localization, they are what you are, they encode the Worldsheet instanton corrections. And another feature of these results from supersymmetric localization is that you can actually access, in principle at least, all the regions in the moduli space. So you're not using the GLSM as a method to compute quantum corrections in Calabi-Yaus does not necessarily restrict you to a geometric regime. So here we have a window, so it's so to say, to the more exotic regions of the moduli space. And in using the fact that all the regions are connected, we will be able to compute results also in more exotic regions. And actually we'll find interesting structures there. Okay, so the new ingredient to GLSMs from the past few years is that we can compute quantum corrections in Calabi-Yau compactifications directly from results of the supersymmetric gauge theory. Okay, so of course there are geometric regions in the moduli space, and there we don't necessarily need the gauge linear sigma model to do these kind of calculations, because we have a lot of other tools for calculating quantum corrections in string theory. So tools like this include toric geometry, topological string theory, mirror symmetry. We know we can compute higher genus invariance there. So this is well understood in the geometry. And the question, or one of the questions or motivations of our work was to find out if the structures that we know in geometry or in geometric regions of the modular space are also visible in non-geometric regions of the modular space, in these exotic regions. And there's a very good reason to believe that this is the case. So one is, of course, the Worldsheet CFT, because the CFT doesn't really care if there is a geometric space-time interpretation or not. And since you have a CFT at every point in the modular space, it shouldn't be surprising that even though you may not be able to access these regions by geometric means, that they cannot be that different, because they're all Calabi-Yau CFTs. And then also the results from supersymmetric localization point in the direction that even though the phases of the gauge linear sigma model, the regions in the modular space may be exotic, like hybrid regions, Landau-Ginzburg regions, whatever quantity you want to compute, which has instanton corrections, cannot look that different depending on where you are in the moduli space, because they all have this common UV origin, which is the supersymmetric partition function in the GLSM. So so what we considered is, let's take these partition functions in the gauge linear sigma model, evaluate them in different regions in the moduli space, and recover or find universal structures in the corresponding IR theories. So that's essentially what we've been doing in these two papers. So what kind of structures did we find? So we were focusing on the sphere and the hemisphere partition function of the GLSM. And we claim, or this is kind of the conjecture, that when you evaluate these partition functions in different regions in the moduli space, the quantum exact result has the same structure in every phase. And the question is, what are the ingredients? And actually there's a lot of mathematics and physics and ingredients available that are actually not tied to a geometric setting. And so for instance, yes?
Can you go back one slide back?
Sure.
When you say non-geometric setting means Landauer's phase, for instance.
Yeah, Landau-Ginzburg or something more exotic like hybrid phases, like in Landau-Ginzburg model phi, but over something geometric.
I see, I see. How about conical point? Do you have some insight of
conifold points will not be here. So the conifold regions would be at the boundary.
Okay.
So you can actually access those. So in 2016, Emmanuel, Mauricio, and I wrote a paper where we actually used the localization to approach the conifold region for the quintic. But yeah, this is not what I'm going to talk about today.
Oh, okay. But everything becomes singular at the conifold point.
Everything becomes singular at the conifold, but you can still use localization results and make sense of the results, at least in an example-based level. Yeah.
And this chamber structure, how does it arise? Like, for instance,
I will give an example.
Okay, like a flop transition or so.
Yeah, yeah.
Oh, okay.
So it's really flops or generalizations thereof.
Okay, thanks.
So no conifold transition, for instance, because the Hodge numbers will stay the same.
Okay, thanks.
All right, good. Let's continue. So we were looking for sort of structures in the results of these partition functions that are the same in every region of the moduli space, irrespective of whether we have geometry or not. And the ingredients, they come, say, or the structures come from conformal field theory itself. But also when we look at the quantum corrections, FGRW theory, Van, Jarvis, Rahn, and Witten, they have more or less defined structures that are known from geometry, like Romo-Witten, enumerative geometry, like Romo-Witten theory, for Landau-Ginzburg-Overfold models. But also made an entrance as objects that appear in a fairly general mirror construction due to Givental, which is called the I function and the J functions. And what will also be important when we consider D-branes is categories. So D-brane categories are something that are not necessarily geometric. So of course you have categories whose objects are geometric, like sheaves, but you can also have something more abstract, which doesn't necessarily relate to geometric branes. And we see when we consider the sphere and the hemisphere partition function that certain ingredients keep appearing no matter whether you are in a geometric phase or a non-geometric phase of the gauge linear sigma model. And that is a certain state space associated with a pairing. The I and J function, which are objects defined in playing a role in Givental's mirror constructions. The gamma class, so a topological invariant, and if you have D-branes, additional data for the D-branes. And none of this is specifically relating to geometric settings. So these are all these things you can define even if you're not in a geometric setting. So here are the results, or at least a sketchy version of the results. If you take the hemisphere partition function of the gauge linear sigma model, it takes as an input a brane, and conjecturally it computes the exact central charge of the corresponding D-branes. We find the following structure. So we'll have some kind of a pairing associated to a state space. We have a Chern character associated to the brane. We have the gamma class, and we have the I or the J function that enters in here. And it doesn't matter in which region of the moduli space we evaluated, our conjecture is that you will always find this. And in the second paper, my student also worked this out in the context of the sphere partition function where you do not have any branes. And there we also see some structure where the I function, the gamma class, and a certain grading operator that you have on the state space always appear. And actually for the sphere partition, so for the hemisphere partition function, we mostly focused on on Landau-Ginzburg points. But for this sphere partition function, we could also make a few statements about theories which are even more exotic, for instance, hybrid regions, which are not quite Landau-Ginzburg and not quite geometric. All right, so yeah, this concludes my lengthy summary. So if you're fed up, I think this is probably all I have to say. And for the rest of my 40 minutes or so, I'm going to spend to fill in some technical detail and explain more about the quantities that enter into this formula. All right, so please ask questions if you have any. and otherwise I will go on.
So
Okay, so at first I want...
For S2, yeah. S2, you have a pair between I function, right? I bar.
Yeah.
So after pairing, does gamma function disappear? Or
yeah, so what we are observing or how we're interpreting this, it doesn't really appear, and I haven't been clear about what this pairing is. So these are the gaps I still need to fill in.
Oh, okay.
So when you have a sphere, what you actually should be pairing is a state and its CPT conjugate.
Okay.
And so which is essentially is complex conjugation in this case.
Yeah.
And actually also results from mathematics, for instance, by Iritani, tell us that this conjugation operation in this space is a bit more complicated. And actually this is where this quotient of the gamma class and this grading operator seem to appear.
Okay.
So they will be there, and they will be also in this formula. So if I come to that, please ask again when I've filled in a few more details. All right, good. Let's go to a few technicalities. So I first want to recall the definitions of the sphere and the hemisphere partition function, and also answer the question on how this chamber structure appears in a simple example. So this is a rather general and mathematical, and also from a physical standpoint, incomplete definition of a gauge linear sigma model. I'm only introducing the quantities that I will need for my discussion. So at first we need a gauge group, so a compact Lie group. And then I'm introducing a complex vector space, which will be the space of the scalar components of the chiral multiplet. So I'm not introducing any fermions because sort of you will only see, we will not see them or need them explicitly. Then I have some matter. So we have the chiral fields. So there is a matter representation. And this is where the Calabi-Yau condition comes in. So I'm going to impose a sort of a restriction on the property of the matter representation, namely for it to be a map from the gauge group into SLV, not more generally into GLV. And that is sort of encoding the cancellation of the axial anomaly, which will give the Calabi-Yau condition. Because it's a 2,2 supersymmetric theory, we also have a U1R, a vector R symmetry. And I will call the corresponding R charges of this chiral scalar fields Ri. And then for the definition of the sphere and hemisphere, I also need the maximal torus. So we're choosing the maximal commuting subgroup of the gauge group and the corresponding Lie algebras. And then actually the weights of these representations, these are the gauge charges of the fields phi I, and they live in the dual of the complexified version of the Lie algebra of the maximal torus. So similarly, now we need the coupling constants, the Fi theta parameters, which we will identify with the Kahler moduli of the Calabi-Yau. So they take values in the dual of the maximal torus of the gauge group, and they are complex numbers, and I will call the real part theta, and then there is a theta angle, which, well, I call theta. And these I will identify with the Kahler moduli of the Calabi-Yau. So these are my coupling constants. So because it's a gauge theory, we also have a gauge multiplet, and that also has scalar components, which I call sigma, and they take values in the Lie algebra of the maximal torus. And you see that we have the Lie algebra and its tool appearing here. So there is a natural pairing, and when I write things like Q of sigma or T of sigma, what I mean in my notation is a pairing between the Lie algebra and its tool. So this is just notation. And because I'm mostly going to focus on compact Calabi-Yaus, I will also, this is realized in the GLSM by a non-zero superpotential, which will depend on these fields phi, so some polynomial in the phi. And to be consistent, this needs to be gauge invariant. It has to have a fixed R charge, which I fixed to be 2. So this is the vector R charge. And yeah, I will always assume that this is non-zero. So what we want to do when we study a GLSM in this corresponding setup is we first want to find the classical vacuum. And so we write down the scalar potential of the theory, which looks like this, and we set it to 0. So the first term here that includes the sigma fields only. Then we have some terms which mix the sigmas and the phis. And then we have the standard D term and F term equations, which I will detail in the next slide. So what's important here, the classical vacuum will be at u equals 0. These are some of quadratic terms. So in order to get u equals 0, each of them has to vanish simultaneously. And there are different types of solutions to this equation, and that will define for us the Coulomb branch and the Higgs branch, and also mixed branches of this supersymmetric gauge theory. So what I want to focus on mostly here is the Higgs branch. So on the Higgs branch, the sigma fields will all be 0, and we do not have any of these terms here, and the vacuum will be determined by the D term and the F term equation. E for E, I haven't said that E is the gauge coupling. It will not play a role for the sake of this discussion here. So on the Higgs branch, we have to solve the D term and the F term equations to get to the classical vacuum. And the D term equations take the following form. So this is a very compact notation. I will give an example a bit later on, which is a bit more explicit. So this is a moment map equation, depends, it's a real equation, depends on the chiral scalars. And this is now important for understanding the chamber structure. On the right-hand side, we have the real part of this complex coupling constant. So these are the Fi parameters. And typically on the Higgs branch, that's why it's called Higgs branch, the gauge symmetry is broken, completely broken or broken to a discrete subgroup. And yeah, so we have to solve this equation. And then of course we also have, if we have a non-zero superpotential, we also have to solve the F term equation. So that gives us the vacuum, and you see, because this parameter enters here, what kind of solutions to these equations we have will depend on the value of this Fi parameter. And this is how we probe the moduli space. So this is the real part of the Kahler modulus, so to say. So that's how we can move around in the moduli space. And so and that's what defines these phases of the gauge linear sigma model. And that's what gives the chamber structure. And the classical vacuum are also defined as the solutions of these equations, and you can write them down formally here. Just as a comment, if you know geometry, the second equation here, for the special case of a gauge group being some power of U1, would return for you, if W is equal to 0, the definition of a toric variety as a symplectic quotient. So in this way, we can sort of construct the Calabi-Yau via the vacuum equation of a supersymmetric gauge theory. So I will do the quintic in a second. I just want to make another comment about the phase boundaries. So now we have seen that we can have different solutions in principle, depending on the values of our parameters. What about the phase boundaries? So, and that is in the GLSM encoded in the Coulomb branch of the theory. So the Coulomb branch is when all the chiral fields are 0, and actually classically also zeta has to be 0. And then at the classical level, the sigma fields, which are now non-zero, can take any value. And actually there is an unbroken maximal U1 subgroup of the gauge group that is left. And if you analyze the theory, actually you get a potential for these sigma fields. So there would be singularities because the sigmas are unconstrained. You would have non-compact directions. So if you take into account quantum corrections, actually they generate an effective potential for the sigma fields where this Fi theta parameter enters. And then the Coulomb branch will be lifted everywhere except at the critical set of this one loop potential that you get on the Coulomb branch. And that is actually what defines the boundaries of the chambers that I had before. So by finding the Coulomb branch, you can actually find the singularities in the moduli space, the singular loci. And in the GLSM, you do this via this effective potential on the Coulomb branch. So that will not play so much of a role for the rest of the talk. All right, so that was a lot of abstract theory. Let's do the quintic. So how do we get the quintic and how do we map out the moduli space using the gauge linear sigma model? So at first, we have to choose a gauge group, which in this case is U1, so as simple as it gets. Then we need to pick a field content. So we have 6 complex fields, Px and suggestively x1 to x5, which have gauge charges -5 for the p fields and +1 for the 5x fields. So you see that they sum up to 0, and that is the Calabi-Yau condition. So GLSMs where the gauge charges sum up to 0 are Calabi-Yau GLSMs. Then you need a gauge invariant superpotential, and you can convince yourself that this is something you write down. You are linear in P, and you have a generic degree 5 polynomial in x1 to x5. That you don't have anything non-linear in P is due to the fact that you also have to fix an R symmetry, which I haven't really said in detail, but this is, if you also distribute the R charges properly, you will actually find that this is the most general superpotential you can write down. So it's already very suggestive of the quintic. You have a homogeneous degree 5 polynomial multiplied with P. So this is indeed what happens. So if I now go to the Higgs branch and consider set the sigma field, so there would be a single sigma field, but that won't make an appearance. So if you go to the Higgs branch, these are the D-term equations. So the coefficients here, these are the charges of the fields. So this is the in this example, the D-term equation I'm looking at. And you see that the solutions to this D-term equation will crucially depend on what value this real number zeta, which is the single Fi parameter I have in the theory, is taking. So if zeta is positive, then it's not possible that all the x's vanish simultaneously, because then the left-hand side would be negative definite, whereas the right-hand side would be positive definite. On the other hand, if zeta is negative, then you're not allowed to set p equals to 0, because otherwise you wouldn't find the solution. And this tells us that this parameter space will be split up into 2 chambers, which have very, very different properties. And then the F-term equations are what you think they are. So let's discuss the phases step by step. I already said quite a lot of the necessary ingredients. So for zeta larger than 0, actually you find this, a solution for p equals 0. And if you look at the D terms, you see that you had a 5-dimensional complex space of the x's, but you had the D term forces you to exclude the 0 point. And that makes the C5 here into a P4. And then finally, if you set p equals to 0, there's only one F-term equation left, and that will give a hypersurface equation in this P4, and we have constructed the quintic. But the point is now that you can also have this zeta, this Fi parameter, can also have negative values. So you also get other solutions. And these are the ones that I refer to as, in this case, these are the ones that I refer to as non-geometric. And you need a little more analysis. So the vacuum state would actually be setting all x's to 0 and just having p non-zero. So the vacuum would actually be a point as a solution of this equation here. But it turns out that if you turn on classical fluctuations, this generates a potential. And what you end up with is a Landau-Ginzburg orbifold theory with superpotential G5. So P gets a wave. And you have and actually the gauge symmetry gets broken from U1 to Z5, and you end up with the Landau-Ginzburg theory with a potential given by this quintic equation. So this is the classic Landau-Ginzburg Calabi-Yau correspondence of Witten from '93, and there's also been a lot of activity in mathematics and physics to extend this also to the context of D-branes. And in mathematics, this Landau-Ginzburg Calabi-Yau correspondence at the categorical level goes under the name Orlov correspondence. And yeah, there's where the chamber boundaries. So if you insert for this particular example into the definition of this effective potential in the Coulomb branch, and you find the critical points, you will actually see that there is only one point where you have a Coulomb branch in the moduli space at a specific locus of theta angles and Fi parameters, and this is the mirror of the conifold point. So, and you see that you can smoothly interpolate between Landau-Ginzburg and Calabi-Yau in the moduli space because there is only one singular point in between, so you can avoid it. And of course, there are also non-trivial monotomies that could happen and that bring a lot of super interesting extra structure when you try to transport D-branes from Landau-Ginzburg to Calabi-Yau and back. So this is the structure, and this is sort of the more rigorous version of the cartoon that I had on my first slide. All right, so let's move on and add D-branes to the game, because I also want to discuss the hemisphere partition function. So what I will consider in this context is B-type D-branes in a type 2 setting, mostly because I have nothing to say about A-branes. And B-branes engaged linear sigma models are actually very well studied, thanks to a 263-page masterpiece of Herbst, Horry, and Page. They derived for us that a B-type D-brane in the gauge linear sigma model is something non-geometric, actually. It's a gauge invariant matrix factorization of the superpotential of the gauge linear sigma model with a fixed R charge. So what is a matrix factorization, or what is a B-brane? What characterizes a B-brane? So the first you need is some sort of a vector space or a module, which in physics you would call a Chern-pattern space. And it has a natural set to grading. And the matrix factorization is an odd endomorphism of on this module. So a matrix factorization is something rather simple. You take a square matrix with polynomial entries of the chiral fields that you have in the GLSM, and the condition is that this matrix squares to the superpotential times the identity. And sort of any matrix factorization that you can think of describes a different D-branes up to some very non-trivial similarity transformations. So that characterizes a D-brane in a GLSM, and it's not geometric. It's not a sheaf or something like that, and it just would reduce to something like a sheaf when you go to a geometric phase, but not necessarily when you go to a Landau-Ginzburg phase. So matrix factorizations are non-geometric, and in principle, every B-brane that you have in the moduli, in the Kahler moduli space, should lift in the UV to a matrix factorization. And this is actually what Herbst, Horry, and Page told us how to do, and they told us how to transport B-type B-branes between phases of the GLSM, and therefore giving a physics proof of the all-of correspondence using the GLSM. So because you have the supersymmetric gauge theory, the brain will also be charged under the gauge symmetry and the R symmetry, and that is encoded in these conditions. So this defines two matrices, rho of G and lambda to the R, where R is sort of the U1 charge information. So these two matrices, so that just says that the D-brane has to be gauge invariant. And solving this condition explicitly for matrix factorization gives you sort of the gauge charge information of the D-brane. Because we have set our superpotential to have R charge 2, the matrix factorization naturally has to have R charge 1, and that encodes, that's encoded in this information. So I'm giving this definition because these objects, this matrix rho, the gauge charges of the brane and the R charges of the brane, they crucially enter into the hemisphere partition function that I'm about to define. So let me first forget the branes for a moment and come to the sphere partition function. So this is the sphere partition function of the gauge linear sigma model, computed in 2012 by two groups. And actually I've introduced all the quantities that are necessary to here. So what do you have here? You have a constant, which I have nothing to say about. You have a sum over a lattice, and this is sort of an artifact of the fact that we have a gauge field here, and when you put the gauge field on a sphere, it can take discrete values, and this is more or less summing over the discrete values that the gauge connection can take. You're integrating over the space of the sigma fields over the maximal torus of the gauge group. This here comes from integrating out W bosons. The alpha here are positive roots. The M's are the elements of this lattice that naturally pair with the positive roots, and the sigmas are the sigma fields again. And here you have a quotient that comes from the one loop determinants. It's gamma functions, and the dependents are the gauge charges of the chiral fields, and again the sigma fields and the R charges of the chiral fields. And here we have the denominator, and the information about where you are in the moduli space enters here in this factor, which will be responsible for the instanton corrections. So you have the Fi parameter and the theta angle entering here. And this is a complex contour integral. So you're integrating over some contour in the Fi theta parameter space. And this integral has to converge. And this is how you access the phases when you evaluate the sphere partition function. So this object lives in the GLSM, but you can evaluate it in different phases. And you do that by as follows. So the phase is determined by the value of theta, because this was the Fi parameter, which told us in which region of the moduli space we are. And for this integral to converge, you will have to close the contour in a specific way. And that will enclose certain poles of these gamma functions and will not enclose other poles. And so you will get different results depending on how you close these integration contours. And that will evaluate for you these results from supersymmetric localization in different phases. And essentially that can be done explicitly. And the interesting thing about it is that it computes a really, really interesting quantity in string compactification. It has been already conjectured in this early paper, also including Mauricio. And there have been very nice proofs of this also from completely different directions, like anomalies, that the sphere partition function of the GLSM computes the exact Kahler potential on the Kahler moduli space. And these people here, they have used this actually to extract Romo-Witten invariance from the results of the sphere partition function. So this is a really important quantity to compute and interesting to look at. But the point is that you do not necessarily need to evaluate it in a geometric space. You could just as well evaluate it in a Lambda-Ginsburg phase. Okay, so here's the hemisphere partition function. Has also been around for a while by now, and it has a very, very similar structure. The first few terms until up here are the closed string information. Again, you have the Fi theta parameter entering here, which, and if you move that, you will go to different phases, depending on the pole you pick up for the gamma functions here. And then since this is a hemisphere partition function, you have a D-brane, a B-type D-brane on the boundary of this hemisphere. And the information about the D-brane enters in this factor here, and that's why I introduced these matrix factorizations. So if you have a brane in the GLSM characterized by matrix factorization, what you can do, the information of the brane that enters here are these matrices R and rho, which define the gauge and R charges of the D-brane. So you can all compute this explicitly and evaluate this, and also this computes a very interesting quantity, namely the exact fully instanton corrected central charge of the B-type D-brane in the given phase. So
here, trace sub M, M means the one appear in the matrix factorization?
So M is this module, so it's the Chern pattern space.
Oh, okay.
And you have a matrix, which is sort of a linear map on this space, and then you trace essentially over the matrix you get in here. So it's actually, that's what it is. So it's really, everything's explicit. You can write down explicit matrix factorizations, you compute these matrices, you compute these traces. All right, so let me finally come to the content of the papers. Actually, I've been given this talk in 45 minutes. It's amazing. All right.
So we are flexible about time. So it's an online talk.
Yeah, I know, but still, I try to stick more or less to the time. So I'm still on track, more or less. All right. So we just said that this hemisphere partition function computes the central charge of a D-brane. And since we want to compute the central charge in various different phases, which correspond to different worldsheet CFTs, I first want to recall the worldsheet definition of the central charge, which can be interpreted as a disk amplitude. So you have a 2,2 worldsheet CFT, and that has all kinds of chiral rings, CC rings, AC rings. This is the state space of the CFT. And to define the central charge, you take a brane, you take a disk, insert a brane at its boundary, then you stretch the disk and perform a topological twist on the tip and insert some states here. So this stretching and twisting will project these states onto the ground states. And the central charge of a brane is defined as a 2-point function with some operator of a chiral ring inserted at the tip and the brane on the boundary. And that's a two-point function. And what we, and in the context we are interested in, we would consider B-branes, like matrix factorizations, at the boundary and operators of the AC chiral ring at the tip. So in other words, it would be B-branes in the A model. So it's not something that the topological string sees, if anybody's here who likes the topological string. All right, what we considered in our paper was the disk partition function and the central charge in Landau-Ginzburg-Orbifold phases. And our claim is that it can be written like that. So we have a pairing on a state space. We have a gamma class, the I function or J function. I will comment on this, and the Chern character of the brane. So we focused on Landau-Ginzburg-Orbifold phases, and our plan in this paper was as follows. So we wanted to give an intrinsic Landau-Ginzburg definition of the quantities entering into this conjectural formula, and then show that the results of these definitions match on one hand with the hemisphere partition function in GLSM, and on the other hand with results that are known in the mathematical literature. In other words, FGRW theory. And by define, I mean that I can write down explicitly for a large class of models what this I function, gamma class, and so on are based on Landau-Ginzburg data. So the hemisphere will mostly for us be a check that these definitions that we gave are correct, and these structures are appearing. So a lot of data to cover, so I'm now going to go step by step to define what the right-hand side really means. So one of the phases, so we're considering Landau-Ginzburg phases or Landau-Ginzburg-Orbifold, and the data defining this is very, very similar to what we've seen from the GLSM. So you have a superpotential, you have a group, an orbifold group, which we assume to be some discrete group, diagonal only in our case, a matter representation that tells you how the fields are charged under this orbifold group, and the left U1 right R symmetry. And you can also define a state space given on these data. So these CC and AC chiral ring from the CFT map to what's called twisted sectors in the Landau-Ginzburg models. So they are labeled by elements of the orbifold group. And I will call these elements basis elements phi gamma. And I also have to make a technical restriction to a certain subspace of this state space, because actually many things, like in particular the I function and the J function and the FGRW theory, are only defined for a subspace of the state space. And these are called in mathematics narrow sectors. So in the context here, this would be twisted sectors where the only state in the twisted sector is actually the identity operator or the ground state. So this is a technical restriction I'm going to make. And then the pairing would be the topological pairing on the AC ring. And if you take some basis elements of this chiral ring, it's very easy to write that down. So that would be the pairing in our formula. But you have to be careful, because if you go back to the definition here, we have something associated to a B-brane, which will be on one of my slides, be associated to the CC ring, versus the insertion would be associated to the AC ring. So actually, in order to use this pairing on the AC ring, there is a non-trivial spectral flow happening somewhere in the definition for the result to make sense. And this is also something we really observe in our paper. So just to make that clear. So I also have to define the D-brane, and it has been known for a while, since Kapustin and Lee and in 2002, that in Landau-Ginzburg orbifold models, B-branes are also described in terms of matrix factorizations. And the data is exactly the same as we've seen in the gauge linear sigma model, only that it's now in the Landau-Ginzburg context. But we still have orbifold charges and R charges in the Landau-Ginzburg context of the brane, and the matrix factorization will be a matrix factorization of the Landau-Ginzburg potential, so the one without the P field. But we still have a Chern pattern space, and the structures are all the same. And then actually in 2004, Walcher has already told us how to compute the Chern character of such a D-brane, and that can be done by a nice residue formula. And what happens here is you take a bulk state, which can be, in this case, in the CC ring. That's why I made this comment before. And you take this H, or this orbifold representation matrix, and multiply it with some anti-symmetrized power of the derivative of the matrix factorization with respect to the chiral fields that it depends on. So this is a residue formula for a central charge, and you see it's for a Chern character of a brane. You see it's absolutely nothing geometric. You're not integrating something over a form or a cycle or something. And it turns out to be the Chern character of the brane. And I think by now, if I go back to the formula, I've told you what the state space is, I've told you what the pairing is, but I still have to tell you what the gamma class and the I function are. And for that, actually, we have to take into account marginal deformations away from the Landau-Ginzburg point. And well, one of the main results of our paper is that for a large class of models, you can encode the information of this required that we require about these deformations into a matrix with rational entries, which has size h, which is the number of marginal deformations, times n plus h, where n is the number of the chiral fields that we have in the Landau-Ginzburg model. I'm not going to give any details on how to get this matrix, so I would have to refer you to the paper or make one of my co-authors give the talk. And this matrix can be used to define both the gamma class and the I function. So the gamma class is an endomorphism on the state space that acts diagonally, and we can write that down explicitly using the components of this matrix Q. So it's not really clear what I'm writing here, I'm aware. So delta would be the corresponding twisted sector, and K would be an integer lattice, and we give a prescription in the paper on how to relate the set of Ks that are in here, so this angle here means the fractional part of something, to a specific twisted sector. And in the end, we will have a gamma, sort of a component of the gamma class associated to each twisted sector, because this will be somewhat periodic on this lattice. And similarly, we can also use this matrix Q to define the I function. And this is the formula that we propose, tested in many, many examples. The I function can be expanded in terms of a basis of this chiral ring. And the components can again be given in terms of this matrix Q that we defined. And the Q without an index here is the left R charge of the chiral fields. So it's quite complicated, but you can go through the various models. You use the data that I've given you, and it will compute for you the I function. So one comment for those people who know about the Givental mirror construction. So associated to the I function, there's also a J function. And going between the I function and the J function amounts to choosing flat coordinates on the moduli space. So this going to flat coordinates in this context would mean that the corresponding deformation parameters would be the marginal deformations associated to the CFT. I may not have stressed this, so this I function depends on some parameters U, and that would be the moduli that we have. So these parameters will be the deformation parameters for marginal deformations, but sort of in the wrong basis from the CFT point of view. So that you can actually give a prescription given the Landau-Ginzburg data and the state space, how to extract these flat coordinates given the information in the I function, and that will give you the J function. People who know mirror symmetry will know that this coincides with the mirror map. If you want to use this result here to extract Romo-Witten invariants, which you can do from the I function, then you have to make this transformation to flat coordinates. And these are also the good coordinates from the GLSM point of view, because the I function will then encode certain correlation functions that count, define the Romo-Witten invariants. All right, so what did we do in the paper? We showed that these Landau-Ginzburg quantities are consistent with what has been defined in FGRW theory. That includes the I function and the gamma class in Landau-Ginzburg orbifolds. And we actually even, our definitions for the I functions slightly generalize the definitions of for the I functions that were given, or like at least the examples that are more general than what has been defined in FGRW theory. Of course, we've also shown that the hemisphere partition function, the GLSM, reproduces the results the formula for the central charge gives. You can, by evaluating the hemisphere partition function, you obtain the result from this formula, which we now can purely evaluate in the Landau-Ginzburg phase. And then finally, we've tested this in examples for up to 4 Kahler moduli, and we actually also computed the enumerative invariance there, which would be called FGRW invariance. So this would be the analytic continuation of the Romo-Witten invariance to the Landau-Ginzburg point. All right, I'm short on time, so I'm only having a few sketches on what we did for the sphere. So we were a bit less ambitious for the sphere, so we didn't aim for defining all these quantities in different phases, but we mostly showed that when we evaluate the hemisphere partition, the sphere partition function in different phases, then we also always get the same structure. So to recall, the definition of the Kahler potential is very similar from the worldsheet perspective to what we've seen from the hemisphere. So you take a sphere, you stretch it into a cigar, you do a topological twist on the right and an anti-topological twist on the left. All these procedures will project you to Raman-Ramon ground states, and you compute this, this amplitude. And 0 and 0 bar are related by CPT conjugation. What David and I did is we considered GLSMs and phases of GLSMs that are some Landau-Ginzburg orbifold with orbifold group G fibered over some base manifold. So that would be a little more general like than a Landau-Ginzburg model. So, and it includes complete intersections in toric ambient spaces and Landau-Ginzburg orbifolds as special cases. So the complete intersection would be if you do not have a Landau-Ginzburg vibration and you just have a Calabi-Yau, and Landau-Ginzburg orbifold would be a Landau-Ginzburg vibration where the base manifold is a point. And everything in between would be called a hybrid model. And what we found is that when we evaluate the sphere partition function, in these phases, you always get this structure. So you get a sum over twisted sectors coming from the orbifold. You get an integral over the base manifold of this vibration. You get some grading operator that is related to the state space. You get gamma classes, which now depend on the twisted sector and the cohomology classes of the base manifold. And you get sort of the I function times its complex conjugate squared. So this is the result we get on the nose from the sphere partition function. And then we try to reinterpret it also as some sort of a pairing. But it's a bit ambiguous. So we have to be a bit careful because essentially what the sphere partition function compute is the pairing after it's been evaluated, and we may have missed some structure here that we cannot see using this approach. So I already said what a Landau-Ginzburg phase would be. So B would be a point, then the definition of the I and J function, grading, pairing, gamma class coincides with what I've had before. In geometric phases, B would be a complete intersection Calabi-Yau, G would be trivial, then the pairing would be actually what's called the Mukai pairing. This is the geometric setting. And also there, the I-J function grading operator gamma class has been long before, and you can defined long before, and you can actually find the definitions in the book by Cox and Katz on mirror symmetry, for instance. So our results then suggest what I've had on the previous slides, that the CPT conjugate of this sort of states with the I function should involve the gamma class, and that is actually consistent with results in papers by Halverson, Yokostapan, and Morrison in 2013, and mathematical results of Iritani. So again, we have these gamma classes appearing in here. So what we did, or what David did in this paper, was we tested this for many GLSMs. So there is a class of 1-parameter gauge linear sigma models associated to 14 1-parameter complete intersection Calabi-Yaus. And that has all types of phases, Landau-Ginzburg, hybrid, and even more exotic hybrid phases that were discussed for the first time by Aspinwall and Plesser in 2009. And we observed this structure in all the phases, including geometric Landau-Ginzburg, but also in hybrid phases. And the structure and the I function and the gamma class in the hybrid phases, which would be something new because have been for some of these examples defined in 2013 by Emily Clater, who's a student of Rans. So also this result maps with FGRW theory, so we get out the I functions. And we've also done a 2-parameter, one of the standard examples of a 2-parameter Calabi-Yau hypersurface, which has geometric Landau-Ginzburg and hybrid type phases. And there we have new conjectural results for the I function and the gamma class in multi-parameter hybrid models. So this is still open. This is not known in mathematics. And this is sort of one of the conjectures we got out of these calculations from the gauge linear sigma model. So with that, I'm almost on time and done. What did we do? We conjectured universal expressions for the hemisphere and sphere partition function in phases of, in this case, abelian gauge linear sigma models. We've shown that these, we have collected a lot of evidence that this works, at least in geometric Landau-Ginzburg and hybrid phases. So we're covering a lot more space of the moduli space than one usually considers. And our results also match with mathematical results from FGRW theory. Mirror symmetry were available, and we tested this for a lot of non-trivial examples. And then finally, there is, I think, quite a lot to do. So some questions, some of these may be interesting for physicists, others for mathematicians. One is the appearance of this gamma class, and that's still kind of a mystery, in particular in the context of world-sheet CFTs. So that would be an interesting conceptual question to understand. Something that I've been heavily involved in and which has been a very interesting topic also in algebraic geometry is to extend this discussion, for examples, in non-abelian gauge linear sigma models that leads to rather exotic Calabi-Yaus that are not sort of related to toric geometry. So I think this should be straightforward, but it's technically very challenging. Something that's more for the mathematicians, it's called broad sectors, and I think mathematicians are having interesting new results in this context. So I made this technical restriction on only reducing to a subspace of the state space when I defined the I and J function for the Landau-Ginzburg model. So lifting this restriction, I think, gives very interesting, would give very interesting new result and would sort of complete the discussion for the most general Landau-Ginzburg orbifold models. And then what I'm personally very interested in is to study these hybrid phases, which are sort of, everybody knows that they are there, but not many people are studying them. And I think with these techniques, it would be possible to understand, for instance, branes in hybrid phases and also enumerative invariants like generalizations of FGRW invariants in hybrid phases. The mathematicians have already defined those, and it would be interesting to compute them. And yeah, there are also more results in localizations floating around. So maybe these structures that we found for the sphere and the hemisphere can also be found in different results from localization. And yeah, if you're mathematicians, you may also be interested in trying to prove any of the conjectures that we have here. So in particular, also this appearance of the gamma class is something that mathematicians seem to find quite interesting. And yeah, that's it. Thanks for inviting me, and I'm happy to take questions.
Thank you very much. Questions? I have one question. When you said you just changed from I to J for Landau-Ginzburg orbifold, you can extract Gromov-Witten invariants, right?
Yes.
So what does it mean? I mean, there's no geometry behind it's Landau-Ginzburg model. Gromov-Witten invariants or what?
Yes, so that's the point, and there's actually a lot of mathematical structure behind that, and this is the main work of FGRW.
Okay.
So they actually defined and tell you what the enumerative problem is on the Landau-Ginzburg side, and they define corresponding invariants, which are called FGRW invariants, which would be analogs.
Okay, so when you said Gromov-Witten invariants, it's FGRW
invariants.
Okay,
sorry.
okay,
so it's Gromov-Witten invariants in geometry and FGRW invariants in Landau-Ginzburg.
I see. Can you relate the Gromov fit invariance in geometric phase and then FJRW invariance in Lana-Ginsburg phase?
So it depends on what you mean with relate. So they
And for instance,
can be
quintic, I mean,
computed, but I don't know if I have an invariant which you could, for instance, understand as a certain two-point correlation function topological gravity, and I transport it there
yeah.
and to see if I get another invariant. I don't know if I could do that.
Oh, okay, I see. I see. Mm-hmm. So when you say narrow phase, so you pick some particular element in this orbit production?
Yes. So
delta
you
mentioned.
that you can understand in many ways what these narrow states are. So in Landau-Ginzburg context, that would be, so you have these twisted sectors, and these twisted sectors contain various ground states. And the narrow sectors would be those sectors which only contain one ground state, which is the identity. So that also simplifies, for instance, this residue formula here, because you have the identity. So this is not a generic situation. And the correspondence of this in, for instance, geometry would be that you have moduli which in a Calabi-Yau that do not descend from the ambient space. So that's sort of the Landau-Ginzburg analog of this.
I see.
And usually when we have, for instance, in geometry, toric geometry, we usually use the ambient space for everything. And for instance, the modulus on the quintic can be related to a divisor on the Calabi-Yau, which comes from the ambient space. So this would correspond to things that are also hard to understand in geometry. So the Landau-Ginzburg theory itself can deal with these so-called broad states without a problem. I mean, Intelligator and Wafa have defined pretty much everything, and you don't need a restriction. But when it comes to deformations and the definition of the gamma class and the I function, you need the restriction.
I see.
As of now. So I think this is a work in progress.
I see. One more question. So when you said you check this I function, you define I function for Landau-Ginzburg, and you check it by using GLSM description. So you just substitute particular value of Kahler parameter of this hemisphere partition function coming from exactly. GSM, and that coincides with I function you define?
Yes, yes. So that's what we did. So what we did is we can write this formula here on the right-hand side, purely in the Landau-Ginzburg context, but we can also show that when we evaluate this hemisphere partition function for the parameter region where the Landau-Ginzburg model would sit, we recover the same result.
I see, I see. Okay, thank you very much. Any other questions from audience?
I have one. I have a question. In the sphere case, when you compute this sphere, and so you compute several examples on hybrid phases, right? And you find this structure of some pairing of gamma with gamma conjugate. One page after this, I guess, just to see that formula. That kind of thing. This sphere partition. So I guess many of these, as you said, these hybrid phases are like Landau-Ginzburg orbifold favored over some base manifold. However, there are some Landau-Ginzburg phases that sort of look like that, but they are called these bad hybrids. There's this difference between bad hybrids and good hybrids. I think this came up on the Aspinwall and Plesser.
Yeah, so we also looked at those, and the thing
what
is,
happens?
So what happens is that, what Aspinwall and Plesser sort of said is that the structure of these phases decomposes into different components.
Right, so what happened with the sphere partition?
So what happens with the sphere is that this sort of generalizes as like this whole expression is like a sum of two expressions that goes over the two components that you have.
Oh,
so we have examples of this in the paper. So it's a bit more general than what what I've been writing here, and sort of you get several copies of this expression corresponding to, say, this kind of weird components that you get from relating back to the fact that the corresponding GLSM has the D-term and F-term equations have different sort of orthogonal solutions in the phase. So it doesn't completely break down, and that's very interesting because the mathematicians exclude this case.
These about hybrids.
Yes. Essentially because you don't have a consistent definition of the R charge.
Oh, I see. That's right. So how that gets solved in this case? Just the two components have different R charges?
So yeah, that's how you would interpret it. So it doesn't really get resolved globally, but somehow locally on each component, you have an R charge.
Oh, I see. So you have to adjust.
This is very sketchy, and I only understand this through very indirectly through the equations of the GLSM.
Well, but still, okay. It's interesting to know that actually that happens.
Yeah, it seems to be so. The GLSM and this partition function indicate that things still seem to work in these models.
Are those models, remind me, that they are argued in Plesser and Aspinwall's paper? Do they argue that they are singular somehow, or they just argue that they cannot analyze them?
Yeah, they do argue that they are singular somehow, but they only have a few sentences about the geometric, sort of the physical interpretation of this. So they behave like, so they have these limiting points, they're at finite distance, so they have a lot in common with conifold points. But,
yes. Indeed.
But yeah, they have some arguments about, the low energy effective theory, saying there's some like SU2 enhancements somehow happening, but I have to admit I've never really understood that. So it seems from all the indirect calculation of the GLSMs that these models seem to make a lot of sense.
But it's an SU2 enhancement on space-time, right?
Yeah, something like that. That's what they are.
Okay, I see.
Yeah.
I see. Okay.
So they have some weird theory of gravity, they're saying. It's like only half a paragraph somewhere in the paper.
Okay. Good. Okay, thank you.
For GLSM, you don't have this gamma over gamma star.
Well, I have it indirectly.
Okay.
So this is sphere partition function, and it does come from, it's produced from this somehow.
But here you have to sum over flux M, and once you perform how to say the sum over flux, you get the pairing between I functions. That's what I thought.
Yeah, so you have to be careful. So there's quite a lot to do to evaluate this in one of the phases. And actually it has been it's a really, really tedious calculation to sort of re-encode the information that comes from this factor, divided up into what belongs to the I function and what belongs to the gamma class.
Okay.
So that actually took us quite a while to figure out how to do this.
Okay,
so
I only deal with like a very simple.
In those spaces many times, but it was really a non-trivial step to see this. So
I see.
It's quite involved, actually.
I see. Okay. Any other questions? Okay, if not, let's thank the speaker for whatever method. Thank you very much. So I will turn off the switch off the recording and leave the space for informal discussion.